Okay, let me do the screen share. Yes. Great. So let's start the date. Good. So today we are continuing the lecture from previous session, in which we were talking about fixed parameter algorithms and the hardness for that. In particular, we talk about vertex cover both in terms of fixed parameter algorithms as well as hardness, as well as kernelization for that. Now, we talk about a particular problem which was very important, which is the multicolored clique. And what was the problem? The problem is that you are given a vertex of input graph G, that are colored with K colors, and we want to find a clique containing one vertex from each color. So you can define the same problem like a multicolored independent set or other things that we have this partition of the vertices into colors, and we want to have only one vertex from each set. Good. Good. Kevin, does it make sense?
Yeah.
Good. Okay. Now, let's consider the problem which is more interesting here. Let me clear everything. So this is a very important reduction that we talk about. The previous time we mentioned that the multicolored clique and the clique are the same in terms of parameterized reduction for FPT algorithm or fixed parameter tractable algorithms. Here, I want to talk about another problem, dominating set. And we discussed about like some assumptions like clique or ETH is the one that's the problem hardness assumptions. Now, and we talk about parameterized reduction. So here we want to give a parameterized reduction. Let me bring it up. Good. So we want to say there is a parameterized reduction from multicolored independent set, which is the same as multicolored clique, to dominating set. So that's a very important reduction. What is a dominating set? So dominating set is a set of vertices in the graph S, such that each vertex, either it is in the set or one of its neighbors is in the set. So that's the definition of a dominating set, which is a very important problem. It's very closely related to the concept of set cover, which is a very important problem. Good. Now, let's do the reduction and see how can we get the result. So what do we want to solve? We want to give a reduction from multicolored independence. So it means that we want to solve a multicolored independent set using dominating set problem. Good. So let's G be a graph with n vertices and m edges and k be an integer, like this is the k color that we have. Now we try to construct a graph H from G that such that if G has a multicolored independent set of size K, then H has a dominating set of size K, and vice versa. Good. So this is G. So for G, we want to solve essentially multicolored independent set. And then we create a graph H, for which for H, we try to create, we want to solve dominating set. Good. So what is G? Let me just delete some part of it. Good. So what is G? Though in G, we have this K guys. So there are K sets here. Now, let's create H out of it. So yeah, this is the graph G that we talk about. It is color K. And we try to create actually graph. I think here we will call it a graph G prime actually instead of H. So how do we create it? So the first thing is this one. For every vertex V belong to vertices of G, we introduce a vertex V in G prime. So for each vertex here, we are putting a vertex in graph G as well, G prime as well. So this is G prime. So any vertex V here, we are putting a vertex V here. Now, we have a set Vi. So these are V1 to Vk here. For any of these Vi's, we are making this one clique. So these vertices, we are putting it, and we are adding all edges in between. So we make this one clique. So each vertex has a corresponding things here, and we are making this one clique. So that's the second step. There is a third step. For every I, so these are like the cliques that we are creating here. And these are all of them are connected. Now, for every of, use another color for this one. For every of this clique, we are adding two vertices, two other vertices. One is xi, and the other one is yi. And these are connected to all vertices of this. This is actually x1, y1. And in general, if this is the one, so these are connected to all vertices here, xi and yi. So that's the third step. Now, what is the fourth step? The fourth step is that we need to model the edges. So whenever there is an edges here between these two vertices here, between U and V, say this is VI and this is VJ, then we are creating a vertex WE. So, and then say this edge is E. So we are adding a vertex here. So this is, say, this is I, and this is Vj. So this is, say, Vi, and say this is Vj. So we are adding a vertex WE, and in G prime, and we make it adjacent to every vertex here. So there was this vertex U here, and the vertex V here. So we will make this WE connected to every vertex here, except U, and every vertex here except V. Good. And so that's the last set of things that we have. So again, I will mention that this is the graph G. We have V1, V2 to Vk. These are the vertices we want to solve multicolored independent sets. For each of these Vi to sets V1 to Vk, we are putting the corresponding set with the same set of vertices. For each of them, we are adding these two vertices, xi and yi, that are connected to every vertex here. And in addition, for each edge that we have it between two vertices uv in the graph, which is in the vi and vj, so we are creating a new vertex, we, that is connected to every vertex in vi except u, and every vertex here in vj except v. Good. Now, what is the claim? So the main claim is this one. So the claim that G has a essentially multicolored independent set with exactly one vertex from Vi, if and only if G prime has a dominating set of size K. And of course, for this problem, K is somehow just a number of sets in the partition. Here, dominating set K is given to us. So we want to see whether there's a dominating set of size K. And again, dominating set is the problem that each vertex, we need to essentially select the set S such that every vertex either is in the set or it is adjacent to one of the vertices in the set. Good. What is the main claim? The main claim is that, so we have K sets here. The main claim is that a dominating set of, so this is the claim. It says that a dominating set of size K has exactly one vertex from each Vi. And this is the corresponding vertex that would be independent set in the original graph. Note that here also there is one difference. So all vertices Vi here, there is no edges between them because we want to create essentially independent set that contains only one vertex from each of them. And here we are making everything clique. Good. So that's essentially the whole proof that we want to show, that any dominating set of size K has exactly one vertex from each Vi. Good. So this part is easy, that you need to select at least one vertex from each of these sets. Because in particular, if you consider X like xi and yi, and the vertices here, you need to have at least one vertex to cover them, because either these guys should be in the set, or and one option is that you will select yi to be in the set, but in that case, xi, that's the thing that we are putting two vertices. Then in this case, xi also should be in the set as well. So then you have two vertices, but the total budget that you have is K. So in some sense, that's the main reason that you need to select one vertex from each of these guys, because if you don't select anyone here, then you need to select both xi and yi here, and then the total things, because for each of these sets you need to do that, then the total budget would be more than K. So the wise things, if you want to have a budget of K, is that exactly you will select one vertex from each of these guys, because of this construction that we have. So that comes from the fact that here it is a clique. We need to select essentially one vertex here. If you don't, there is some possibility that you want to select some other vertex from other thing that covers this. But in that case, if you don't select any guy here, in the set Vi, then you need to select both Yi and Xi because you need to cover them because they don't have any other neighbors than this. So you really need more than one, and the total budget here is one. And that's the main reason that actually you need to have exactly one from each of these sets. Does it make sense? Good. So, now let's go to the next step. So the next step, we didn't mention about the dominating set. So what about the dominating set property? And so the dominating set says that from each vertex should be either in the set or one of its neighbors should be the set. Independent set here is that there are two vertices U and V that they have an edge, you can select only one of them. And we want to say that this is equivalent in these two problems. Good. So why is it the case? Now, it is exactly because this construction of WE. Each edge that you have it here, as I mentioned, we have a vertex WE corresponding to that here. And as we discussed, for each of these V1 to Vk, we need to select, just draw it with this different color. So for each of them, we need to select one guy. Now, the main thing is that we want to make sure that if two vertices U and V, they have an edge between them in the original graph, you should not select both of them in your dominating set. And again, these are two different properties. One is dominating set property, the other one is independence. However, this has come actually exactly because of the construction of WE. And that's actually one of the nicest trick here. So here we know that this WE, so okay, if we want to select this U and V here, that U and V have an edge here in the graph. It means that this WE corresponding to this edge does not have any vertex, does not have any edge adjacent to U and no edge adjacent to V here. But the issue is that this WE should be covered in the dominating set. Either it should be covered itself or one of its neighbors. So here we knew that we have only, we have one vertex from this Vi, one vertex from Vj, and these two are U and V. But we know that WE, because it was corresponding to an edge between U and V, does not have any edge to Ui or to U. It doesn't have any vertex to any edge to U or V. So it means that in this case, we need to include actually WE itself in the set. And again, we mentioned that you can have at most one vertex from each set Vi, Vj. So it means that it would be more than the budget K that we have. So the only way that we can have a dominating set of size K here is that no edge in the original graph that we have, we should select both endpoints. So that's exactly the definition of independent set. And that shows actually that dominating set and multicolored independent set in terms of the parameterized reduction are the same. Everything that we have, so we actually, the parameter K here is exactly the same parameter K here. So we didn't have any blow up in parameter K in terms of N or anything. So it is exactly K is the same K here. And every other thing that we have done it, all things were polynomial in N and K as well. That shows that independent set and dominating set, actually it shows that in some sense, dominating set is a harder problem than independent set. Now, let me clear everything. And as I mentioned, so we have shown actually this dominating set is as hard as independent set, and you can similar things. You can say that an independent set and Clique are the same. We can show that the other problem like set cover, hitting set, connected dominating set, and independent dominating set, and partial vertex cover. You can see the definitions like in the book or online, they say that all of them actually as hard as independent set or clique. So clique is a very important problem here because all of this problem shows that it is as hard as clique, or independent sets are the same. So this is a good exercise. Prove that there is a reduction from dominating set to connected dominating set and set cover. So what is the connected dominating set is that these vertices that you are selecting in the graph, they should form a connected, all of them should be connected as well in the original graph. If you consider these vertices that you have selected for your dominating set, there should be a set of edges in between in the original graph such that the whole thing becomes a connected graph. This is a connected dominating set. And a set cover I have mentioned is very similar to a dominating set. In this problem, you are given a sets here and elements here. And here, each set is attached to the elements here. You want to select the minimum number of sets here such that you cover all elements. What's the meaning of covering all elements? Means that the union of this set should contain all these elements. So these are the sets, these are the elements, and we want to make sure that the union of these sets is covering all the elements. So this problem, you can show that actually there's a parameterized reduction from dominating set to both of these problems. This problem is very similar to dominating set indeed, because all of these elements should be covered. But here, you cannot select an element here. You should only consider sets, and you should include sets. And you can think about them. Good. Now, we discussed about the assumptions, and we mentioned that the main assumption here is that exponential time hypothesis, that for n variable 3 set, there is nothing better than 2 to the little o of n. Good, and we mentioned that there is you can say that there is another assumption, Clique assumption, that for k clique or k independent set, there is it cannot be solved in f of k n to the order 1. Essentially, the best thing that we hope for is something like n to the k for the problem. And you can show that if you assume the ETH, actually that also gives the k clique. Hopefully, if we have time, we will go through that as well. Now, what we learned that there is this problem of independent set or clique, which are hard problems, and the multicolored version are equivalent to just no colored version. And there is this other problem, dominating set, which is harder than clique. So that's the for understanding so far. So the main question is that, like, dominating set or independent set, these are the problems which are both NP-hard problems. And here we showed that, so what we showed that in some sense, dominating set, let me just say, so we showed that the dominating set somehow is harder than independent set. Independent set, or essentially clique as well, these are the same. I mentioned, because you can just take the complement of the graph. But the question is that, what about, can we show that also independent set is as hard as dominating set, the one that we have shown for independent, for NP hard set of problems, or NP complete set of problems? Interestingly, so far, we cannot do that. And actually, the current situation is that indeed, dominating set is a harder problem than independent set in terms of parameterized complexity. So in particular, we know that independent set is W1 complete and dominating set is W2 complete. And what is the W0? W0 are essentially the fixed parameter algorithm. So those algorithms that essentially there is f of k n to the order 1 time algorithm for the problems. So we know fixed parameter algorithm, those that we can actually get f of k n to the order 1 or fixed parameter algorithms. Independent set is W1 complete and dominating set is W2 complete. But let's define W1 and W. So to do so, first you need to define the Boolean circuits. So what is a Boolean circuit? So Boolean circuits, essentially it has some input gates. This is just a circuit. I mean that you should be familiar with the circuits. So people at Zoom, does it make sense, everything so far?
Yeah.
Good. So here, this is just a regular circuit that we have. We have the input, and we have AND. This is AND. This is OR, and this is negation. So far, it's like essentially a circuit, and say that at the end we can have, so we have some input and the output is just 1 bit. 1 bit output. Now, what is the circuit satisfiability? That's a very important problem. You are given a Boolean circuit C, like this one, consists of inputs, 1 output, and this set of AND, OR, and negations. You want to see, can you assign to this x1, x2, essentially true or false? And true and false will be considered 0 and 1. 1 for true, 0 for false. So you want to see whether you can give 0, 1 here, such that the output is 1. Or like you want to give 0, false, like true and false, such that at the end the output is true. So that's a called circuit satisfiability problem. Now, what is the weighted circuit satisfiability? So that's the part that actually comes from the fixed parameter tractable things. You want to satisfy this circuit. So in the weighted circuit satisfiability, you want to satisfy circuit with at most k ones, or k true essentially. So you want to say the number of ones that you are putting should be at most k. That's the one that is called weight k. Good. So that's the one that is called weighted circuit satisfiability. And that is k essentially is the parameter size that we are talking about. Now, so we have defined the Boolean circuits, circuit satisfiability, and weighted circuit satisfiability. Now let's go and define give more definitions such that we can define W1 and W2. Good. So we had the weighted circuit satisfiability. Now, what do I want to show? I want to show that independent sets can be reduced to weighted circuit satisfiability problem. So essentially, I need to create as well as dominating sets. So for both of them, I want to say that actually I can solve these problems by solving some problems, some circuits. How can I create a circuit? Say, consider, for example, for independence. So for independence, that is easy. So I will put x1, x2, x3, and xn. These are corresponding to the vertices that I want to select. So I have a graph G. This is a graph G, actually. And this is the example. So from this graph G, for each vertex, I will put essentially an input, x1 to x, and corresponding to v1 to v. Now, what is the circuit that I'm doing that? So I will first get the negation of this. And then I will, for each edge in the graph, for example, here, you consider the edge v1, v3. So here, between v1 and v3, I will connect the negations of these guys, and I will take the OR of these guys. So for each edge, I am doing that. For example, here, I mean, these are some of the things that I have done it. So if say this is the Vn, for example, there is a edge between V2 and Vn. So for V2 and Vn, I'm creating another this one, and so on and so forth. Then I will take AND of everything. So this is a negation, OR and AND. Now, I want to say that this problem, if I have an independent set of size K, and you can think about here exactly K. If you have an independent set of K that satisfies the circuit, it means that the output is 1. Yeah, so I want to say that, yes, if there's an independent set of size K, then I can put K of these inputs true such that the output is true. How can I do that? Of course, just select those vertices on the independent set in this case. So for example, here I say that I will consider V1 and V2 as to be independent set. So I will put it X1 equal to 1, X2 equal to 1, and everything else equal to 0. And of course, there are K of them. So lots of this parameterized complexity, actually, the parameter K may remain the same, exactly the same K, or it's linear. Good. Now what will happen? The thing that happens here, and it is interesting, is this one. So let's see what is this role of these guys. So the role of these guys is that the main issue is that, so what is the independence? That you want to make sure that no two vertices that they have an edge should be selected. So consider here, for example, V1 and V3. So V1 and V3, there is an edge between them. We want to make sure that in the independence that it should be not the case that both of V1 and V3 are selected. So if both V1 and V3 is selected here, so if this is 1, so let me just do it a different color. So this guy is 1. This guy is 1. Then, so both of them become negation. So it becomes 0, becomes 0. Now, then you will take OR of 2 guys, and the OR of 2, 0 would be 0. And then you will take AND of some guys, and if there is 1, 0, then the whole thing would be 0. And you can see that. And so if this is the case, if 2 of them got selected, but you can see that if one of them at least not selected, one of these, when you take the negations, at least one of them in the OR would be 1, and then there is no problem for the AND as well, because all of them should be 1. So this shows actually that independent sets, you can define it using a circuit. Now let's do the same thing for dominating sets. How can we do that? Again, consider this graph, V1, V2, V3 to Vn. And I want to create a circuit here. So again, the same thing that we have done it for each vertex, I will put an input there. And the parameter K would be the same for the weighted circuit satisfiability and K dominating set. The only thing is that, so what are the AND and ORs? So here, what do I do? For each vertex in the graph, I will put an OR. This OR includes the vertex itself and all its neighbors. And then I will take the AND of everything. Let's see what will happen for this example. So we have this V1, V2. Okay, so I put one input for each of these vertices. Now, V1 is connected to V2. So I will put for each vertex, so here, essentially, for each of these vertices, for example, for V1. For V1, I will put an OR here, and it is connected to itself and all its neighbors. So its neighbors is V2 essentially. So you can think about actually each vertex has a loop to itself. So in that sense, actually the dominating set would be, it says that from each neighborhood of each vertex, one person should be selected. So this vertex, because there's a loop from a vertex V to itself, it means that you can select V itself or one of its neighbors. So here it says that for X1 and X2, I mean, like one of these vertices should be there. What about V2, for example? So V2 is connected to V1, V3, and Vn, and of course it is connected to itself as well. So then it means that this V2 is connected to all of them, and one of them should be selected. So here there is no negation. It means that if one of these, so for each of these OR guys, one of them should be 1. It means that one person should be selected. And then you will take AND. It means that all neighborhood should be satisfied. Here, the same thing that we had it for independence, that all edges should be satisfied. So that's the one that shows that, okay, now if there are K dominating sets, K vertices here that you can put it 1, the rest 0, such that this guy becomes 1, then we have the result that we want. Good. So is the reduction clear from these problems to weighted circuit satisfiability? People in the class seem happy. What about the people on Zoom? Does it make sense?
Yeah, it's clear.
Good. So let's go to the next thing. So I have just mentioned these things. So I have mentioned that these problems actually can be represented by, so graph problems, I can represent them by circuits. Now for circuits, there are two important parameters that I need to define. One of these is concept of depths. So depth is easy. Is the steps of a circuit is the maximum length of a path from an input to the output. So essentially, you can consider this one as a DAG, because I mean, if you consider from top to bottom, you are always going from top to bottom. So it is the whole thing is a DAG, is a directed acyclic graph. Then you consider from any input to output, see what is the maximum length of the, what is the maximum number of these circuits, that would be the depth of that. There is another parameter width. So this W1 or W2 that I have mentioned, that actually comes from this concept of width. That's a very important one. So width of a circuit is the maximum number of large gates. So what is a large gate? A large gate is the one that has more than 2 inputs. So the same way that we define depth of a circuit, we can define the width of a circuit. Width of a circuit is that you, so in the depth, we are counting every circuit, every gate. In the width, we only count the number of large input degree guys. And large here means that greater than 2. Let's see an example here. So in this case, the depth of this circuit that we had it for independent set would be 3. Because here we'll see that there are 3 gates. For example, if you consider this path, there are 3 gates and the maximum is 3. So depth is 3. What about width? So here you will say this is vertices. These both have the 1 input. These guys have 2 inputs, so we don't count them. The only guy that has a high input more than 2 is this AND gate. So the width actually here is 1. Now let's go to this problem, dominating set. So what is the depth of this? Depth of this problem actually is 2, because you have 2 sets here. So the depth is smaller than independent set. And note that I mentioned that independent set is an easier problem than dominating set. Well, in terms of depth, actually, depth of the dominating set is less than that. But the one that makes these circuit problems complicated is the number of high degree vertices, and again, large degree vertices, which are the degree is greater than 2. What is the width of this? The width of this is that each of these neighbors, if you see, they have also large degree, and this guy and guy has large degree. So the width here actually is 2. So this is dominating set. And here, for independent set, the width is 1. So depth is important, but width is more important. That's essentially the class of, now by this definition, I can define the class of W hierarchies. So let me do you hear me? Just, I got some.
Yeah.
Okay. And you hear me well, correct?
Yeah, everything is
good. Yeah, great. So that is good. Yeah, because I got something that I have been logged out. I want to make sure that there is no discount. So here we have this kind of W1 and W2 that we want to, or W3 actually. So we need to, let me clear everything. So how can we define this class of W1 on WT, or essentially WT? So let's define CTD be the set of all circuits having width at most T. As I mentioned, width is more important, and depth at most D. So that's a circuit of T and D. T is the width and D is the depth. Now, a problem is in the class WT if there is a constant D. So as long as it is constant that holds for all input instances, that should be correct. So for example, for dominating set, it was the depth was 2. For independent set, it was depth 3. So as long as the depth is constant, we don't care. So depth should be just constant. The main thing is that, the problem is in the class WT, if the D is constant, any constant, it is important. And then there should be a reduction from this problem P to the weighted circuit satisfiability of CDT. So actually it should be CTD. So again, a problem is in WI or WT. If you can represent this problem with a constant depth circuit such that the width is T, is all at most T. So this is the class of WT. That's the reason. And as we saw, essentially, independence is in the class W1. Again, the depth should be constant. The width is the one that we are parameterizing it. That. So independent set is in W1, and dominating set is W2. Good. And actually, also one important thing, the FPT, generally, when we have fixed parameter algorithm, these are actually in W0. Why they are in W0? Because in the sense that, like for all of these problems, for FPT, we can solve them in polynomial time. For a fixed parameter selectable algorithm, we can actually create a table that we can create a circuit such that the depth of that, so this is the depth actually. So this is the depth and this is width. So here, I mean, sometimes it has been like essentially mentioned in the other direction. So we can write it essentially. So we can create for fixed parameter algorithm some circuits that their depth would be f of k, but their width would be 0. And what is the idea of the VF0? Because in some sense, we can create a circuit, a computer essentially program. So from this program, actually, you can create the circuits that each step uses the previous step. So you can represent the whole computation as a circuit. So this is the similar things that Stephen Cook is doing actually for MP hardness. So it goes from computers, essentially, or from circuits, it goes to computers or vice versa. So the dips of that would be corresponding to the time. And why the width is 0? Because when you do the computations, you can actually represent all these computations by some bit operations that have only input 2 essentially. So all computation can be done with some gates that the input is at most 2. That's the reason that W would be, the width of this circuit would be 0. So fixed parameter algorithm, the depth of them would be order f of k, but the width would be 0. You don't need any high degree gates to do that. So we have the fixed parameter algorithm. So what is the fixed parameter algorithm? For example, vertex cover that we discussed. So vertex cover is in W0, dominating set is in W2, and independent set is in W1. So that should go here actually. You can also prove that independent set is a W1 complete. What's the meaning of W1 complete? It means that not only it is in W1, but it is as hard as any other problem in W1. The same thing you can show that for dominating set in W2. And you show that dominating set is a W2 complete. It means that dominating set is not only W2 and we can represent it. That's actually the easy one. But we can show that it is as hard as any other problem in W2. So we have, in some sense, we have independent set as a complete problem. So we say that W1 complete. And independent set and dominating set is W2 complete. And of course, fixed parameter algorithm are just these guys. Now the question is that what about W3 and so on and so forth? We have actually these classes of W1, W2, W3, W4, and so on and so forth. But interestingly, and you can define some problems which are in any WI. However, interestingly, almost all problems that we are considering are either W1 complete or W2 complete, or they are FPT. So there are not too many natural problems which are W3, W4, or W5 complete. So what do we know about this WT, guys? So we know that all this, one thing that we have we know that the WI is a subset of WJ for I less than or equal to J. So they form essentially a hierarchy. So we have the W0 is a subset of W1, is a subset of W2, and so on and so forth. So, and all of these reductions that we talk about, the completeness of, for example, independent set or dominating set, all of them are parameterized reduction. The one that we discussed. Generally, they should not change the parameter. The change of the parameter should be only f of k, no n involved. As I mentioned, most natural problems actually are contained in the class lower levels, W1 or W2 or fixed parameter algorithms. So we talk about these guys. Now, after that, so this is like continues like this, that this is W3 and so on and so forth. Now, all of them would go to the class XP. So what is the XP class? XP is the class of all parameterized problems that can be solved n to the f of k. So this is the XP. XP essentially said that, okay, the running time of your algorithm would be n to the f of k. Of course, for almost all problems, we have these XP things that you want to see whether the clique of size k, you can just check all n choose k sets, which is n to the k. So this XP is essentially generally the most trivial things that you can do for a problem. So all of them, this W1, W0, W1, W2, W3, and all of them are a subset of XP. And these are the problems that can be solved in n to the f of k. And here, actually, we will show that clique or independent set are this type of problems. So what is the belief? The belief is that W0, W1, W2, and all of them should be different classes. And indeed, for these problems like independent set or dominating set, there should be no fixed parameter algorithm. And actually, the best thing that you can do is these trivial things of the XP. You can just do it n to the k. That's the whole idea of this parameter algorithm. So the problem, either they have a fixed parameter algorithm or they are in one of these W classes, which means that you cannot do anything better than n to the k. So in some sense, there is no backtracking algorithm that can do much better or the much smarter things, at least in the worst case. So let me clear all the drawings here. Good. Let's see whether I can mention this one. Good. So let's talk a little bit more about these things. Now, let's talk a little bit. So we talk about these classes, W1, W2, others. We talk about fixed parameter algorithm. We talk about the parameterized reduction, which was very important things for all of this W1, W2, W3, so forth. And FPT, the parameterized reduction, plays a very important role. And now let's talk a little bit about the assumptions. We talk about these things that about exponential time hypothesis. So this exponential time hypothesis introduced by Impliazzo et al. What does it say? I mean, we have seen it before. There is no 2 to the little of n time algorithm for n variable 3 sets. And there is a stronger version of that set things, a strong exponential time hypothesis. Now, consider the 3 set problem. So if you have n variables, then with these n variables, if you consider the clauses, you can have n to the 3 clauses. So this is, we are talking about the 3 sets here. Why? Because any n choose 3 of these guys that you will consider it, they can form 1 clause. And of course, even it's a negation of them, you can consider it. Like if you consider 2n variables, both positive and negative, 2n choose 3, these are the number of clauses, which would be n to the 3. So when we talk about n variable 3 set, actually, so there are 2 parameters here. It is like n and m. N for the graph. So n is the number of vertices, number of edges can be n to the 2 here. When we talk about 3 set, n is the number of variables. but the number of clauses, which is somehow kinds of hyper edges, can be n to the 3. However, in Piliazzo et al., they showed that there is a if there that this is if and only. If there is 2 to the little O of n time algorithm for n variable 3 sets, then there is 2 to the little O of n time algorithm for m clause 3 sets. And vice versa. So in some sense, because of this if and only things, it means that ETH also says that, so this is a stronger statement. It says that there is no 2 to the little O of m time algorithm for m clause 3 sets. So here in the ETH, we are talking about the number of variables. Say, okay, there is no 2 to the little O of n. But as I mentioned, m, the number of clauses, can be actually omega of n to the 3. But because of this theorem that they show, this if and only if, it says that actually there is no 2 to the little O of m time algorithm for m clause 3 sets as well. Good. So this is somehow even stronger, but somehow equivalent to exponential time hypothesis. Now, there are some, so this is the version that we want to work with it, this version of ETH. Now, there are some classic reductions, MP hardness, that from 3 set to 3 coloring. So there is so if the 3 set instance has essentially n clauses, n variables and m clause, you can turn into 3 coloring problem. So in some sense, so what's the meaning of reduction from 3 set to 3 coloring? It means that 3 set can be solved by 3 coloring. But you construct a graph. What is the size of this graph? The size of this graph would be order n plus m. N is the number of variables and m is the number of clauses in the 3 set. So the number of edges and the vertices in this graph, when you do that, I mean, this is like, you can just search, I think we give a reference in the book, but also you can see the reduction from 3 set to 3 coloring. These are the regular MP hardness things that shows essentially 3 coloring problem is as hard as 3 sets, or 3 coloring can solve 3 sets. When you do that, you create a graph because the 3 coloring is a graph. In that case, the number of edges and the number of vertices of this graph that you construct would be order n plus m, where n is the number of variables and m is the number of clauses. So in both cases, the number of edges and the vertices would be order m. So now, and so in some sense, these are the sparse graph. For them, the number of vertices and edges would be essentially the same, and both of them would be order of m. Now, we mentioned that this ETH says that there is no 2 to the little O of m time algorithm for m clause 3 sets. This actually implies that there is no 2 to the n little O of n time algorithm for 3 coloring of an m vertex graph. So this is also, I mean, this, you can say that this MP hardness reduction also is the one that keeps the parameters the same. So what is the result or the summary of discussion? It says that there is no 2 to the little O of n time algorithm for 3 coloring of an m vertex graph. This comes from the ETH. So in some sense, from the SAT problem, this problem talks about the SAT. From SAT, we are going to coloring, and in particular, 3 coloring. And we say that there is nothing better than 2 to the n, essentially, algorithms for this problem. Now, so we go essentially from SAT we say that from the SAT hardness, ETH for SAT, we can get essentially the corresponding problem for tree coloring. So there is no, there is no like 2 to the little of n or m here. And here also it implies to the m here. And then it means that no 2 to the little of n for tree coloring. This is a graph problem. Now, so we have the ETH, then from ETH, because of this explanation that I have mentioned, we can go to tree coloring. And now, there are standard polynomial time reductions from tree coloring to many other problems. And that actually shows that so because there are standard polynomial time reductions from tree coloring to many other problems, these and all of them, the reduction, they increase the number of vertices by at most a constant factor. So it means that so this is the one more general corollary of that. So these are all of these polynomial time algorithms more like the NP-hard problem that they don't change the parameter and they increase the vertex size only by a constant factor. It means that assuming ETH, there is no 2 to the n little 2 to the little of n time algorithm for n vertex graphs for this problem, like independent set, clique, dominating set, vertex cover, Hamiltonian path, feedback vertex set, etc. So you cannot, this also says that, I mean, in general, even for vertex cover, how we could get fixed parameter algorithm, like we could get 2 to the k times n. But in general, for n, we cannot do it better than 2 to the little o of n. This cannot be better than 2 to the little o of n. So this reduction can give this one that if you consider the k version of these problems, there is nothing better than 2 to the little o of k for this problem. So we consider the ETH. ETH talk about n. There is no parameter generally for this problem. I mean, the parameter can be n essentially. And these reductions that we are considering actually shows that we cannot get anything better than 2 to the n for these problems. The same type of reduction, as I mentioned, these are somehow, they are preserving the parameter k. So they imply also there is no better than 2 to the little o of k, n to the order n, n to the order 1 algorithms for k version of this problem. So in some sense, we talk about vertex cover, and I mentioned that there is like, we discussed about 2 to the k times n, and we mentioned that we can do it 2 to the k times n, and then I think the best one is 1 to the 2 to the k times n. But we cannot get for this problem something like 1 to the 2, I don't know, square root of k. Except this might be possible only for some graphs like planar graphs. And for planar graphs, also, the main thing that the reason that we can get square root of k, because planar graphs generally, planar graphs have a linear number of edges. And while the general graphs can have a quadratic number of edges. So that's the reason that this quadratic versus linear is the difference between this hardness of like nothing better than 2 to the k for vertex cover in general graph versus 2 to the square root of k for vertex cover on planar graphs. Great. Now, what else we can get it? So this one, so far we talk about 2 to the, so we mentioned that, for example, for vertex cover or dominating set or other, this one, we cannot get better than 2 to the k. Of course, for vertex cover, we can get 2 to the k times n to some constant. But for dominating set or independent sets, we cannot get fixed parameter algorithms. So this is not strong enough for us. However, there is this other theorem that, what does it say? It says that ETH implies clique hardness. What's the meaning of that? This is a theorem that was stuck 2004. Say, assuming ETH, there is no f of k n to the k algorithm for k clique for any complete function, any computable function f. So what is the meaning? So we have, so far we consider this problem. We talk about ETH. From ETH, we could get some hardness of like 2 to the k, nothing better than 2 to the k times n for general graphs or for these problems. However, this holds both for vertex cover and dominating set and independent set. But we know that independent set and dominating set, these are harder problems. Can we get any harder results? That indeed we have it here. So this problem is said that assuming ETH, actually for independent sets, here in this case, we talk about k clique, which is the same as k independent set. For this problem, you cannot get anything better than f of k times n to the order little o of k algorithms. That's indeed something stronger that we have it for these problems. And we will talk more about this one next time. So that's essentially the things that we have shown some hardness for all of these problems. For vertex cover, in some sense, the situation is tight. We cannot get better than 2 to the k, 2 to the little o of k, and we can get 2 to the k because it's a fixed parameter algorithm. But this is not tight so far for dominating sets or independent sets or clique, which are the same. So like independent set and clique are the same. This theorem says that actually ETH implies a stronger things, that for dominating set or independent set, both of them are W1 and W2. And as I mentioned, dominating set is indeed harder than W1, and dominating set is indeed harder than independent set. But anyhow, for both of these problems, you cannot, under ETH, we cannot get anything better than f of k times n to the little o of k. So in some sense, if somebody gives you k dependent set, k dominating set, the best thing is that you just try all possibilities. There are n choose k possibilities, just try all of them and see whether any of them essentially is an independent set or dominating set. And that's the thing that we will talk. And we will talk about this. We are talking about the hardness of kernelizations. And we talk about the connection of fixed parameter algorithm with approximation algorithms and streaming that we discussed before. So that we will continue in the next session. And I think we are done for this session. People in the class, if you have a question, please let me know, or the people at Zoom, if you have any question, please let me know. Seems there is, yeah, so that sounds good. So it seems there is no other question. So let me stop share here, and then we will continue with this one to finish this area of hardness for fixed parameter algorithm or parameterized complexity. Thanks everyone, and see you next time. Bye.